In this video, we'll introduce a new NMR experiment called carbon NMR or carbon-13 NMR. This is going to be different than what we've been talking about up to this point. We've been talking about proton NMR or hydrogen NMR and looking at the signals that come from the hydrogens. But obviously, organic molecules contain other nuclei besides hydrogens. We can study those too by NMR, so that's what we're going to talk about in this video. Okay, so just to get an idea of what we can see by NMR and what is not possible to see by NMR, in general, only nuclei that have odd numbered masses are NMR active. That would be hydrogen, carbon-13, fluorine-19, phosphorus-31. These are the ones that are by far the most commonly studied isotopes. So by the same virtue, right, if you have an even mass of your nucleus, those generally are not going to be seen in the NMR. That's why we use deuterium as a solvent in proton NMRs. And carbon-12 won't show up in carbon NMRs just because it has an even numbered mass. The problem is that pretty much 99% of carbon atoms, or 99% of naturally occurring carbon atoms, are the C12 isotope, and only 1% are C13. So the problem with carbon NMR is that there's a low relative abundance of carbon-13, so we need high concentrations, or we need longer experiment times to get decent resolution because there's not as much carbon-13 naturally occurring in the molecules. Okay, so let's compare a proton NMR and a carbon NMR and look at some similarities and some differences, right? So we're familiar with the proton NMR of ethyl acetate. We have this set of hydrogens and this set of hydrogens and this set of hydrogens, right? And this gets split by adjacent hydrogens and this gets split by adjacent hydrogens. So we see three signals here. But notice there's 1, 2, 3, 4 carbons that are not chemically equivalent. And chemical equivalence for carbon NMR is exactly the same as proton. So none of these carbons can be interconverted through mirror planes or rotational axes. So now in the carbon NMR of ethyl acetate, we see 4 signals for each unique carbon. But notice that there's no splitting. So the first thing that you want to note about carbon NMR, no splitting, all singlets all the time. Okay. Also, while it's possible to integrate proton NMRs, you're never going to integrate carbon NMRs. So the only thing that we're really going to be looking at in carbon NMR is a chemical shift and chemical equivalence, which essentially tells us the number of signals that we'll expect. Another major difference is the scale is much different. While we're still in parts per million, we go from about 0 to 200 or 220, whereas for proton NMR we're going from about 0 to 12. So those are the main differences there. Okay, so just like in proton NMR, where we had characteristic regions where we'll see different kinds of hydrogens, same thing happens in carbon NMR. So a carbon that's part of a carbon-oxygen double bond, a carbonyl carbon as they're called, are typically going to be seen in this region between 150 and 220. We can actually even break this down further and say that between about 190 and 220 is where we'll see ketones and aldehydes, and between 190 and 150 is where we'll see things like esters or amides. So if we have a hydrogen or a carbon here, it's going to be further to the left. If we have an oxygen or nitrogen here, it's going to be further to the right. And then other sp2 hybridized carbons, or carbons that are part of a carbon-carbon double bond, are going to be in this region between 150 and 100, so we'll call this sp2. Then we have our sp, in addition to sp3 that are bonded to an electronegative atom, so that could be nitrogen, oxygen, or a halogen. And then here's where we're going to see our sp3. So again, the position relative to one another is the same. You see sp3 first, then you see sp3 bonded to electronegative atoms, then you see sp hybridized carbons, then you see sp2, and then in this case furthest to the left is where you see carbonyl carbons. So again, what you want to look at is electronegativity and hybridization to rationalize where you're going to expect to see various chemical shifts. Okay, so let's take a look at this molecule, right? And let's try to figure out which peaks come from which carbons, right? And then first thing that you want to do is determine the number of peaks that you would expect to see. So we have a carbon here, that's one peak, two. There's a mirror plane that bisects this molecule, which might be difficult to see. So these two carbons are the same, and these two carbons are the same. So we should see 1, 2, 3, 4, 5, 6, 7, 8 signals. We see 1, 2, 3, 4, 5, 6, 7, 8 peaks. Okay, so that's right so far, 8 peaks. Okay, here's an aldehyde carbon. So that's going to be this peak, right, furthest to the left. And then we have a carbon of an ester. That's this one. Now we have 1, 2, 3, 4 aromatic peaks, which are going to be right here between about 140 or 100 and 160. These two are going to be these two carbons, right, because they're smaller. These two are going to be these two carbons. It might be difficult to tell which peak comes from what carbon, but we know all four of these are from our aromatic ring. 1, 2, 3, 4 peaks in the aromatic region. And then we have this peak, right, which is an alkane next to an electronegative atom, so that must be this carbon. And then we have an alkane that's not next to an electronegative carbon, or sp3 carbon that's not next to an electronegative atom. Okay, let's do some more practice. Let's first think about how many peaks that we would see and where we would expect them to be before we move on. So notice that there is a mirror plane that bisects this molecule like this. So these two carbons will be chemically equivalent, so that would be 1 peak, 2, 3, 4. So we should see 5 peaks, right? And then these two should be further to the left in this region between about 60 to 100. Okay, and then we should see 1, 2, 3 other peaks in the alkane region, or the sp3 region. So let's see what that looks like. We have 1, 2, 3 peaks from 1, 2, 3 sp3 carbons, and then we have 1, 2 alkyne peaks. So that's exactly what we predicted. Okay, let's look at another one. Okay, how about this molecule, right? Well, one thing that's really confusing for some people is symmetry in terms of these aromatic rings. So another way to draw an aromatic ring, which might be easier to see that there is a symmetry plane here, is to just draw a circle in here. And so there is a symmetry plane that essentially goes through here and then through here. So we have 1, 2, 3, 4, 5, and then all these carbons are chemically equivalent 6. So we should see 6 peaks, right? 4 of those peaks are going to be aromatic peaks, so we should see 4 aromatic peaks in that region between 160 and 100. And then this is a carbon that's next to an electronegative atom, so that'll be about 60 to 100. And then this signal will be between 0 and 60. Okay, so then let's look and see if we're correct. Notice we have one, 2, 3, 4 aromatic peaks. 1, 2, 3, 4 aromatic peaks. Then we have this carbon next to an electronegative atom, right? And then we have these, which are chemically equivalent, which are corresponding to this peak. Okay, one more example. Notice that we have symmetry again, so we should only see 1, 2, 3, 4 aromatic peaks. That's exactly what we observe here, 4 aromatic peaks. We have a carboxylic acid, so that's going to be shifted to the right. We have a ketone, it's going to be further to the left. And then we have this lone sp3 hybridized carbon, which is this one. Okay, so let's put together all the information that we have to really get the most information that we can possibly get about a particular molecule that's under study. So let's say we had an unknown sample that we knew could be either this compound or this compound, right? We take an NMR spectrum, a proton NMR spectrum, and this is what we get. We get a quartet, and we get a triplet, and this should be actually a 6 here. So we get a ratio of 4 to 6, which makes sense, right? In each one of these we should have a triplet that integrates to 6 and a quartet that integrates to 4, because this has a symmetry plane and this has a symmetry plane. The quartet should be further to the left in both, and the triplet should be further to the right, because in both cases they're further away from the oxygen. So how can we tell the difference between these two molecules? Well, the way to do it is to take a carbon NMR, right? So if we take a carbon NMR, notice that in this particular case we have 1, 2, 3 peaks, and notice that one of the peaks is here in the carbonyl range. So this molecule must be diethyl ketone and not diethyl ether. So we can put together information from proton and carbon NMR to solve more complicated problems. Okay, so to summarize, proton NMR. For proton NMR, we're going to use chemical shift, chemical equivalence, integration, and spin-spin splitting all together to get as much possible information as we can. For carbon NMR, we're only going to use chemical shift and chemical equivalence. We're not going to worry about splitting or integration. Those aren't important for carbon NMR. And to get the most information, we're going to combine spectral information from proton and carbon NMR spectra of the same sample.